Robox, optimized robot for lifting soccer ball and place it at a distance. Abstract. Today's technology of robotics and automation has reached enormous advancements. In this research paper we did the designing, calculation and analysis of the robot according to the given problem statement. The problem statement was specified, but we had the target to do the designing with simplest usage of mechanism as well as weight reduction. So, for this we used software such as SOLIDWORKS and ANSYS. Keywords: ANSYS, CAD model, SOLIDWORKS. Introduction. Objective of this project is to create a robot which will be receiving a football coming with a velocity of 4m/s, take it to a box which is at 5000 mm and then drop it into the box whose height is 300 mm. To stop the ball, we have designed two structures keeping in mind that the ball can come either rolling on the ground or in a projectile motion. For rolling, we have designed a seesaw-shaped structure which will allow to stop the ball inside our robot but won't let it get away from it. For projectile motion, we have used a net mounted on a goalpost kind of structure which will stop the ball and drop it in desired place. To take the robot to a height of 300 mm, we are going to use a conveyor belt, inclined at an angle, so that the ball reaches the height of 300 mm and the belt will also be the one dropping the ball into the box. For locomotion of the robot, we are using standard robot wheels of diameter 130 mm. Working methodology. Selecting the mechanism. We decided two mechanisms, first the one we chose and the second was to stop the ball and use a robotic arm to pick it up and put it into a box. We decided on first one because its working was much simpler and implementation was easier as well. Design and analysis. To support the bot, we have made a four-wheel aluminum chassis of dimensions 902 mm x 600 mm and mounted a wheel assembly with wheels having diameter of 130 mm. We have designed a football goalpost-like structure having a net to stop the ball and drop it in desired place. We have also made a seesaw-shaped structure to stop ball, which will come rolling with a speed of 4m/s. There is enough space in between the start of belt and end of seesaw-shaped structure for ball to rest, assuming diameter of ball to be 250 mm. We have made a structure to support the belt and support for ball to go up and mounted the structure on the four-wheel chassis. Belt is going to work with the help of a DC motor. We have also made an inclined support of sheet metal, 584A301, for the ball to go up. And have attached two rotors at the end of it, near the ground, for the ball to easily get on the support. Detailed working. When the ball is rolling on the ground, it will come towards the seesaw-shaped mechanism and will start climbing on it. Once it crosses the halfway of seesaw, the part where ball is going towards will start to go down, and once the ball crosses the seesaw, it will return to its normal position. There is some space in between the seesaw and belt, so the ball will be contained there. In case the ball is coming in projectile, there is a football goalpost-like structure having net on three sides of it. When ball hits the net, its speed will decrease and then it will fall in the space we have left. Even if the ball bounces, it will remain in the space and won't go out of the structure. Once the ball comes to rest, the rotors will help to get the ball on the inclined surface. Once the ball is on inclined surface, we will move the robot and take it to the box at a distance on 5000 mm and of height 300 mm. Once the robot reaches the box, the conveyor belt will start rotating and take the ball upwards on the inclined, and on reaching the end of inclination, the belt will keep on rotating and will drop the ball into the box. Electronic parts. 4 DC motors, 12-24V, four-wheel having torque of 110.5 kg/cm or more and a RPM of more than 400, 2 DC motors, 2 4V, 4 belts, circuit board, proximity sensor, ultrasonic sensor. Components: DC motors, circuit board, wires, sensors units. Specifications. Components specifications. 4 DC motors 12-24V, torque equals 110.5 kg/cm, RPM equals 400. 2 DC motors 2 4V, Torque equals 80 kg/cmt. Proximity sensor range equals 2-4 mm. Ultrasonic sensor range equals 4-5 m. 2 DC motors 1-2 V, torque equals 6 kg/cm. Calculations. For locomotion motors, mass of the bot, 17 kg, acceleration, 2 m/s2. Force equals ma. Equals 17*2. Equals 34 N. Since there are 4 motors, so each motor should supply 34/4 N or 8.5 N of force. Distance, for torque, equals radius of wheels equals 65 mm or 6.5 cm. Torque equals F*D. Equals 8.5 6.5. Equals 55.25 kg/cm. Due to margin for friction and inefficiency in power transmission, taking factor of safety as 2, we get required torque equals 55.25 2 equals 110.5 kg/cm RPM. Diameter equals 130 mm or 0.13 m. Circumference equals pi *d equals 0.41 m. Assuming required velocity of robot as 10 km/h or 2.7 m/s RPM equals 2.7/0.41, *60 equals 395.1. RPM equals 400, rounding off, some common mistakes. For belt drive, radius equals 50 mm, mass of belt equals 4 kg, acceleration equals 2 m/s2. Torque equals 420.05 equals 0.4 or 40 kg/cm. Taking factor of safety 2, we get torque equals 80 kg/cm. RPM. Diameter equals 100 mm or 0.1 m. Circumference equals pi d equals 0.315. Assuming belt velocity to be 2 m/s, RPM equals 2/0.315, 60 equals 381 RPM. For rotors, mass equals 0.3 kg. Radius equals 101 mm or 0.1 m. Acceleration equals 1 m/s2. Torque equals 0.30.11 equals 0.03 or 3 kg/cm. Taking factor of safety as 2, we get torque equals 6 kg/cm. RPM. Diameter equals 202 mm or 0.2 m. Circumference equals pi d equals 0.63 m. Assuming velocity of rotor to be 1 m/s, RPM equals 1/0.63, 60 equals 96 RPM. Insights. Problems faced while deciding mechanism of robot. Deciding which mechanism to go with, conveyor belt 1 or the one with robotic arm. How to stop the ball coming with a velocity of 4 m/s or in a projectile. How to take the ball to a height of 300 mm, meaning whether to keep conveyor belt vertical or to keep it on inclination. Problems faced while designing the robot. What dimensions to take. How much inclination should we give to support and the belt. Specific designs of chassis and parts. How to stop the ball coming in projectile. Measures taken to overcome them. Conveyor belt mechanism was decided due to the ease of stopping the ball and, we don't need to control the robotic arm. We decided on a seesaw-shaped mechanism to stop the ball, if it is coming while rolling on the ground, and a goalpost-like structure with net to stop a ball coming in a projectile motion. Conveyor belt and support were given an inclination as a vertical conveyor belt would have required more power to take the ball vertically up and weight was more balanced in keeping the belt inclined. Dimensions were decided keeping in mind the dimension of ball and maximum dimensions of robot. Inclination of belt was decided on base of its length and part designs were modified during the assembly to incorporate the changes. Point of special mention. We were only considering the ball to be coming from ground, so when we found out that it may come in projectile motion as well, we tried to incorporate goalpost-like structure and seesaw mechanism in a single bot. But we could have also made two different designs, one with seesaw mechanism and other with goalpost-like structure. Result. In this way, Robox was designed with the help of software such as SOLIDWORKS. and the analysis was done in software called ANSYS. According to the problem statement, we designed it in the most optimized way with respect to weight reduction and within given dimensions of 1000 mm x 1000 mm. Fig 1, CAD model. Fig 2, analysis result of basket skeleton. Fig 3, total deformation result of basket skeleton. Fig 4, analysis result of base. Fig 5, total deformation result of base. Fig 6, total deformation result of chassis.